Hello everyone, my name is Patrícia Ferreira and I'm a PhD student in computer engineering. I will be presenting the paper titled Unsupervised Flow Discovery from Task-Oriented Dialogues. This paper was authored by me, Daniel Martins, and professors Alves, Catarina, Silva, and Hugo Gonçalo Oliveira. Task-oriented systems are designed to fulfill specific user tasks or requirements, such as making a reservation or requesting information, to encompass all target tasks along with all possible interactions. Creating dialogue flows for these systems is complex, time-consuming, and often done manually. Moreover, the resulting flows can rarely be shared across domains, meaning that their design has to be performed for each new dialogue system. This is where automatic dialogue flow discovery can play a crucial role. By analyzing the conversation turn history, this task can help identify communication trends that support the design of flows for virtual agents, thus accelerating their processing or aiding in their validation. We propose a generic approach to automatically discover the most frequent flows in a dialogue history and visually represent them as a transition graph. This visual representation allows users to perform a post-inspection of the discovered flow, also useful for audits, and it's an unsupervised approach, making it applicable to any collection of task-oriented dialogue. Dialogues are represented as written sequences of statements contributed by various participants. While our approach is versatile and can be adapted to various scenarios, our main focus is on task-oriented dialogue involving a client and an agent. Here is an example of a dialogue from the multi-was dataset, which was used in our experiment. Dialogues are represented according to their meaning, for example, through their embeddings, and dialogues are grouped based on their semantic similarity, with these groupings representing dialogue states. Transitions between states and their respective probabilities are then calculated. This results in a transition graph with states as vertices and transitions as edges, where there is a probability of transition from one state to another. In addition to the vertices derived from clusters, two vertices representing the start of the dialogue and the end of the dialogue are included. I will now explain the experimental setup that was followed. Okay, the proposed approach is implemented and applied to a well-known dataset of task-oriented dialogues, a multi-was dataset. Its dialogues consist of multiple turns of interactions between two participants, a user playing the role of a user with a task to fulfill, and a system attempting to respond promptly while assisting the user in completing the task. We used version 2.2 of MultiWAS with the test portion for flow discovery. Different methods were tested for the representation, clustering, and labeling of statements. However, except for the latter, we focused on a single implementation and left the comparison of alternatives for future work. For representation, we use the sentence transformer, which converts sentences into vectors. In the second step, any clustering algorithm could have been used, but we opted for the k-means algorithm. For multi-was, the number of clusters, denoted as k, was determined using the silhouette method, which evaluates the cohesion and separation of clusters. Since we always know the speaker of each statement, user and system statements were analyzed separately, resulting in a different number of clusters for each. Here is the scatter plot indicating that the maximum score occurs when k is 18 and k is 13 respectively for the user and the system. These were the cluster numbers used, and two approaches were tested for labeling clusters. One uses the most frequent verb phrases in their statements obtained from Spatie library, and the other is keywords to extract the most frequent keywords in the group's statement. Okay, I will now present our results. This is an example of one of the flows created for the multi-was training data. In it, we identified the start and end nodes of the dialogue. User representative nodes are in light blue, while system representative nodes are in dark blue. This flow not only visualizes the possible paths in the dialogue, but also quantifies these probabilities. It is a valuable tool for guiding and understanding the different pathways from the beginning to the end of the interaction. To discover the labels, we used verb phrases that provide an idea of the system's actions and responses, such as hotel suggestions, available options, or greetings, and reveal the user's needs and intentions, such as searching for hotels, help, and specific information. We can set the threshold to ignore transitions with low probability. In this case, we use the threshold of 0.15. But we can vary the threshold. In this case, with a threshold of 0.10, we see many more transitions than in the previous example. Okay, flow visualizations provide interesting insights, but drawing conclusions about their utility and how they represent dialogues is a challenge. To obtain a quantitative metric of success, we propose evaluating the flow by measuring how well an unseen portion of dialogue, like the test set, follows the discovered flows from another portion of the same type, for example, the training set. For different values of threshold, we calculated the transition accuracy, that is the predicted transitions compared to all transitions in the test set. The higher the threshold, the smaller the graph and the lower the accuracy. With threshold is 0.20, there are no paths between start of the dialogue and end of the dialogue, so no transitions are predicted. With threshold is 0.5, over 80% of transitions in the test set are predicted. Okay, Motivated by the importance of flows in task-oriented dialogues and the amount of manual work involved in their production and validation, we introduced an innovative approach to unsupervised flow discovery. This approach provides an analysis of communication trends and includes three stages: representing utterances as vectors, clustering semantically similar utterances, and finally, constructing a transition graph. The conducted experiments provide a pathway to extract relevant dialogue flows without the need for annotated data. Graphical visualizations offer an intuitive representation supporting both creators and users in interpreting and optimizing task-oriented dialogue systems. This is complemented by the proposal of an automatic evaluation demonstrating that flows represented by 33 dialogue states can predict over 80% of transitions in the test set of Multilaw 2.2. There is much more that we aim to improve and explore. Our plans include exploring different clustering algorithms, investigating alternative approaches for labeling clusters, considering the context of previous utterances, and finally discovering flows for virtual agents that do not rely on task-oriented flows, such as data-driven chatbots, for example, ChatGPT, thereby contributing to their explanation. And with that, I conclude my presentation. Thank you very much. Feel free to contact me if you have any questions or suggestions. Bye.